Assalamu alaikum, dear students. I hope you're all fine by the grace of Almighty Allah. I welcome you all to the 27th lecture of Thermodynamics 2. Lecture 27. The contents of lecture 27 are specific steam consumption, heat rate, regeneration Rankine cycle, overall efficiency of steam power plant, numerical problems, and conceptual questions and answers. So briefly we have discussed regarding the specific steam consumption and heat rate in the previous lectures as well. So we will look into the detail what is the mathematical relation to calculate the specific steam consumption, what are the advantages and disadvantages, what is the relation of specific steam consumption to the efficiency of Rankine cycle, and what does its physical meaning, or what does it relate to the physically the size of power plant as well. Then we will discuss regarding the heat rate or the heat supplied in the boiler. So how does the heat rate relate to the minimum power output of the turbine, and if we want to maintain a certain amount of power generation from the turbine through generator, then what will be the process and what is the required heat rate. Then we will discuss about the regeneration. So what does the regeneration mean, and how regeneration process is used in the Rankine cycle. So we have already discussed about the Rankine cycle. Initially we have discussed regarding the ideal Rankine cycle, and then we have discussed about the actual Rankine cycle. Then we have differentiated what are the parameters that differ in the ideal Rankine cycle as well as in the actual Rankine cycle. Now we will discuss how we can increase the efficiency of Rankine cycle with the help of regeneration process. Then we will calculate the relation for the overall efficiency of steam power plant. What is its mathematical relation? What are the components that contribute to the overall efficiency of steam power plant? Then we will solve some numerical problem, and we will discuss some conceptual question answer as well. Specific steam consumption. So specific steam consumption is also known as steam rate, and by definition, if we want to define what specific steam consumption is, so it is defined as the amount of steam required to generate a unit power of turbine. It also represents the size of power plant. So this is the physical meaning. So as you can see, we will see what is meant by this. So the power generated by the turbine with the help of generator directly relates to the specific steam consumption or steam rate. So the mathematical relation to calculate specific steam consumption or steam rate is that the steam flow divided by W net. So W net is the amount of power that is generated by the turbine. So as you know that I will draw a simple Rankine cycle. So here we have pump, then pump is connected with the boiler, and then here we have turbine, then here we have condenser. So at the inlet of boiler, we have saturated liquid. At the inlet of boiler, whereas at the exit of boiler, Q amount of heat is supplied in the boiler, and at the exit of boiler we get saturated vapor. So the amount of saturated vapor or steam that is entering, so turbine, so here turbine is connected with the generator. Here I will show the generator. So turbine shaft is connected to the generator as well. So the steam flowing through the turbine is known as the saturated vapor that are flowing through the turbine directly relate to the power output through the generator. So the power output is, let's suppose the power output of turbine, if you are talking, so it is has a unit of kilowatts, whereas saturated vapor or steam flowing through the turbine has a unit of kgs per hour, kg per hour. So this is a schematic diagram shown. So you should know that where is the direction of flow of steam and what is W net. So W net, this is W net, that relate, its unit is kilowatt, that is the power output of a turbine, whereas stream that is flowing through the turbine has a unit of kg per hour. So how much kilogram of steam is flowing through the turbine per hour in 1 hour? So the hour term come into the denominator because it's also kg per hour. So in the denominator the units are kilowatt hour. So this is the unit of energy. So usually, as you know that if you look at the electricity bill of your house, so the units that are consumed within a month are shown on the bill in term of kilowatt hours. So here that is the amount of power generated by the turbine when certain amount or certain mass of steam is flowing through it. The unit of SSC or specific steam consumptions are in kg per kilowatt hour or kg per kilojoules. Here an example is shown, that if we have a certain steam power plant, for example, if we talk about the steam power plant and 500 tons per hour of steam. So here the direction of steam 500 tons per hour. So 500 ton mass of steam is flowing through the turbine in 1 hour, and that turbine is generating 1 megawatt of power, and you are asked to calculate the specific steam consumption. So you should be very careful with the units. So you should know that in 1 ton there are 1000 kilograms. So the 500 tons are converted into kg per hour. So in the statement, the mass of the steam is given in tons per hour. But here you should look in the formula, the unit of mass or steam flow is given in kg per hour. So you should be converting the given statement units into the standard units that are used in the formula. So you convert the unit, that is 510 raised to power 3 kg per hour, and similarly you will have to convert the megawatt into kilowatts, because kilowatts are unit are used in the standard formula. So 100 megawatt are converted into kilowatt, and one it is multiplied. So 1000 will cancel out with each other, and double zero will also cancel out with each other. So specific steam consumption or steam rate is 5 kg per kilowatt hour. So this is very important, because it tell the relation, because it tells the relation of steam that is flowing through the turbine with the unit kilowatt hour or unit energy or unit power produced through the turbine. So it means that for every 5 kg of mass that is flowing through the turbine, it is producing 1 kilowatt hour. So usually you know that in the thermodynamics, the specific meaning or specific properties are very important. So for example, we previously we have talked about the specific volume, specific density, so the specific enthalpy, specific entropy. Therefore, specific steam consumption is also very important, because it tells the lowest number or the unit power generated through the turbine or power plant. So how much steam must be flowing through the turbine. So it somewhat relate to the efficiency of the power plant as well. So for example, uh, if we say that for we here we consider two examples. In example 1 kilowatt hour of energy or power is produced with the specific steam consumption of 5 kg, and in another power plant 1 kilowatt hour of power is produced with the specific steam. So here write specific steam consumption at the top with the 3 kg of steam. So this shows the relative efficiency of both these. So this means the second one has higher efficiency, whereas the first one has low efficiency. So here we can have a comparison between the efficiency as well. So now we will look how the specific steam consumption relate to the size of power plant. So we know that efficiency and size of power plant are inversely proportional to each other. For example, if we have so consider this is a size of one power plant and another power plant that is little bigger in size, and suppose they are producing same amount of power. So this is also producing 1 megawatt of power, whereas second is also producing 1 megawatt of power. Its size is 1000 meter cube, for example. I'm just giving you an example, and its size is 1500 meter cube or yards or whatever the units are. I just want to relate the size and efficiency relation with each other. So if we here in 1000 meter cube size, it is the power plant is producing the same amount 1 megawatt, and here the larger power plant is producing the 1 megawatt. So it means the efficiency, its efficiency is greater than this power plant, second power plant efficiency. So for example, this is A and this is B. So efficiency of A power plant is greater than efficiency of B. So specific steam consumption relates that the efficiency and the size of power plant are inversely proportional to each other. If the power plant is more and more efficient, then its size will be reduced with respect to the size of power plant that is large. So in the, if we compare this these two power plants, then we came to know that specific steam consumption of B is greater than specific steam consumption of power plant A. So here power plant B have a specific steam consumption B, and let's suppose it is 5 kg, and here it is 3 kg per hour, 5 kg per hour. So you look that the, as the specific steam consumption is more and more greater, the size of power plant is also increased. So this is a direct relation or the physical interpretation of specific steam consumption. So if you know the value of specific steam consumption of two power plants and they both are different, so you will know that the power plant with the greater value of specific steam consumption will have a greater size. So the power plant with specific steam consumption which have a larger value will also have a larger size of power plant. So heat rate. So by definition, the heat rate of it is the rate of heat input required to produce unit shaft power output. So know that in the boiler, heat is supplied through the combustion chamber or boiler house or whatever mean. So Q amount of heat is added into the system through boiler, which will convert saturated liquid into saturated vapor. And that steam or saturated vapor will then enter into the turbine. The turbine. A turbine is here it has blades that are connected to the shaft, and shaft is generated with the connected with the generator, and generator is producing electricity. So in the previous slide we have related the value of power with the saturated vapor, but the actual energy input is in the boiler. So heat is added in the boiler. So this heat per unit time is known as heat rate. So Q amount of heat is added into the boiler. So we are relating in the previous topic, in the topic of specific steam consumption, we have related the saturated vapor mass to the power generated. Now we are relating the amount of heat that is added in the boiler with the power that is generated. So mathematically, if we are talking about the relation of heat rate, so heat rate is equal to Q1 divided by W net. So W net is the power that is generated, whereas Q1 is the heat supplied. So Q1 is the heat supplied, and W net is the power that is generated. So if we look into the relation of thermal efficiency, so we know that the thermal efficiency is equal to work output divided by work input. So W net is the work output, whereas Q1 is the amount of heat that we are introducing into our system. So thermal efficiency is W over Q1. So we came to know that heat rate is the reciprocal of efficiency. That is the thermal efficiency. So now if we talk about the units in which we supply heat into the system and the units in which we extract work from our system. So we supply heat into the system that have a unit of kilojoules per second, and we extract energy from the system that is in kilowatt. So you should remember, you might be remembering the steady flow energy equation we have discussed in the previous lecture. So that is Q in plus H1 plus W1 is equal to Q out plus H2 plus W2. So here Q in is the Q1 and W2 is the amount of work that we are extracting out. So this equation has a unit of kilowatts or kilojoules per second. So heat that is supplied through the boiler into the system have a unit of kilojoules per second, and the amount of work that is extracted through the turbine from the system has a unit of kilowatts. But usually when we are calculating the value of heat rate, so similarly in the previous slide, when we were calculating the value of specific steam consumption, we have a unit given in kg per second, kg per hours. So here hours are the standard unit. So we have to convert that second unit into hours. So we know that in 1 hour there are 3600 seconds. To convert the amount of heat that is supplied in kilojoules per hour, we will multiply it with the value of 3600. So here we have Q1, which have a unit of kilojoules per hour, whereas W net will remain in the same unit as well. Then the heat rate relation is 3600 multiplied by Q1. So that is the amount of heat that has a unit of kilojoules, and the work extracted from the turbine have a unit of kilowatt hours. And in term of efficiency, if we are given the value of efficiency, then the heat rate will be calculated as 3600 multiplied by efficiency. So 3600 divided by efficiency, so it is a unit of kilojoules per kilowatt hour. Regeneration Rankine cycle. So in the previous lectures we have already discussed the method or procedures that we can be doing to increase the efficiency of a Rankine cycle, which include to reduce the compressor, to reduce the condenser pressure, to increase the boiler pressure, and to superheat the working fluid. So these three methods were discussed in the previous lecture as well. So another method to increase the efficiency of Rankine cycle is the method of regeneration. So in a brief term, the method of regeneration, if someone asks what the regeneration is. So the process of regeneration is to extract energy from one part of a cycle and introduce it to the other part. So in this schematic, so just so you know that the processes that are involved in the Rankine cycle are so here that is a pump. So pump work is here, and then from here this is the boiler work. So energy is increased. Then this is a turbine, and that is a condenser. So what is the difference when we use the regeneration Rankine cycle? So if we look at this schematic diagram, first I will discuss this schematic, and then we will go into the TS diagram as well. So so I've taken this from the internet. So these are the values from the another problem that was in the internet. I've seen that we will discuss in that later topic as well. So these are the temperature written for your reference. So here we have two feed water pump. So here we have a pump, and this is written as feed water heater. So this feed water heater is also known as the regenerator. So in some books it is written as feed water heater, and in some book it is written as regenerator. We will discuss it means the same, um, but why does it call as regenerator, and why it is called as feed water heater. So in a normal when regeneration process is not used in the Rankine cycle, we have a pump that is pumping the working fluid into the boiler. Heat is adding into the boiler. The working fluid before entering the boiler is a saturated liquid, and the working fluid that is exiting the boiler is a superheated or at least saturated vapor. So this is entering into the turbine. So there is an expansion and work is extracted from the turbine, and low energy working fluid is exiting into the turbine, exiting from the turbine and entering into the condenser. For example, if you want to increase the efficiency, so in the previous topic we have discussed regarding the heat rate. So that heat supplied to the boiler is coming from a certain combustion chamber, and we are burning the certain amount of fuel. It may be coal, diesel, or another hydrocarbon. We are burning certain amount and providing it with certain amount of heat. So if we want to increase the efficiency, so one method to increase efficiency is to reduce that Q. That will save some fuel as well. So but we cannot compromise the temperature of the boiler. So if we assume that the working fluid is water, and the at the temperature at which it is exiting is suppose that it is exiting at a temperature of 200 degrees centigrade. So it is written in, let's go with the example uh, numbers. So the fluid that is exiting the boiler has a temperature of 300 degrees centigrade. So if we now consider that there is no feed water heater, and the pump is pumping the water that may have a temperature of 20-30 degrees centigrade. So let's suppose we have to burn 200 or 20 kg of coal within 1 hour to give the certain amount of heat into the boiler to raise the temperature to 300. So now here we will discuss what process is done in regeneration. So in the regeneration process, we just there is a process known as bleeding. So here we will put a small hole in the turbine and extract some energy. So here this process is known as bleeding, to extract energy from a small hole. So a certain amount of steam that is entering, so let's suppose 1 kg of steam is entering into the turbine. So x kg of steam is bleed out through the that small hole and feed into the feed water heater, and rest of the mass of the steam, let's suppose m mass is exiting through the bleeder, and 1 minus m is exiting through the proper channel and entering into the condenser. So let's suppose 1 kg of mass is entering, zero point 0.3 kg is bleeding out through the uh, that hole bleeder and entering into the feed water heater, and 0.7 kg of mass is entering into the condenser. So here we will save energy because the condenser is also a heat exchanger. So here in some process we will be entering a coolant or cooling water, or some device will be connected to this condenser that is taking heat out, or some fan must be flowing the heat, flowing air that is taking out heat from through this condenser. So that energy will also be reduced, because initially it was 1 kg and now zero point 0.7 mass, 0.7 kg of mass is per second is flowing through that condenser. So the condenser work will also be reduced. Moreover, let's suppose after the condenser it is a saturated liquid and the temperature is 20 degrees centigrade, and pump 1 was pumping the fluid into the boiler that is approximate. So here the given temperature is 40 degrees centigrade. We will go with the temperature that is given. So after the condenser, the temperature of working fluid is 20 40 degrees centigrade. So that 40 degree centigrade water with entering into the feed water heater, where 0.3 or mkg of mass per second is entering. So that will be a steam. So steam is mixing with the working fluid. So now you see that here up into the boiler. So look, the steam that is entering is 233 centigrade hot. So the temperature of steam is 233. So it will mix with the water and will increase the temperature of the working fluid. So that is the reason that low amount of heat is introduced into the boiler. So less fuel is burning now, because the water already entering into the boiler has a higher temperature than the previous. So previously the water, when there is no feed water heater, the water that was entering into the boiler was 40 degrees centigrade, and now when there is a feed water heater, the water that is entering into the boiler has a temperature of 233. And also, so we are saving two energy in two steps. So step one is we are introducing less fuel, and we will be needing less heat content will be introducing into the boiler. So the working fluid entering into the boiler is already high temperature, and less amount of fuel is required to increase its temperature. And in the second step, the work done by so work consumed by the condenser will also be less, because there is a less working fluid entering per unit time into the condenser. So little work will be done on the condenser. So that in two step, we are through the regeneration process, we are increasing the efficiency of Rankine cycle. So in the previous slide, we have just considered a single regenerator or single feed water heater, but in the actual process, there may be a number of regenerators that are connected continuously, and for every regenerator, we will have another extra uh, feed pump or heating pump. So 1 to 2, this is an ideal case. So from 1 to 2, it was a pump. So from 1 to 2, this is pump 1, and from 2 to 3, and he from 2 to 3, this is a feed water heater. So pump is introducing. So pump 1 is introducing the working fluid into feed water heater, and from 6, the feed water heater is connected through the bleeder of the turbine, and now the temperature at the inlet of the boiler is this. So I will mark it with the pen. So look at initially at this temperature, the working fluid was entering into the boiler. Now when we have installed the feed water heater or regenerator, look, this is a temperature difference. So this temperature difference is already created with the help of feed water heater, therefore a less amount of work. So you can see initially you can see this is the amount of work that was initially done by the boiler, that is the enthalpy value. Now look, this enthalpy value is reduced. So now boiler is previously was supplying energy from 6 to 2 when no water. So H6 minus H2 was the previous, and now when heater or regenerator is installed, then the boiler is giving or introducing the energy from H5 minus H4. So now we look into the mathematical relation. So Q1 is the amount of heat supplied through the boiler, that is H5 minus H4 when there is a regenerator connected, and WP1 and WP2 are the two pumps that are connected. So enthalpy change for WP1 or pump 1 is because less amount of mass is entering. So just to give a quick, so let's suppose here in the boiler there is 1 kg mass. So this is a turbine. So through bleeder 0.3 kg mass is entering through the regenerator, and 0.7 kg of mass through the condenser. So you see that through pump 1, the mass that because we multiplied with the mass, so enthalpy value is reduced. So value of enthalpy H2 minus H1, that is 2 and that is 1, but because that is 1 minus x, because x is the mass that is flowing through the regenerator. So 1 minus x is the mass that is flowing through the pump 1, and when through pump 1, that is 1 minus x, 1 minus x, and that is x, and through pump 2, this is from 3 to 4 is a pump 2, that is 1 minus x plus x. So x cancel out with each other, then the mass is combined in the pump 2. So that way the enthalpy difference for pump 2 is not multiplied with any x mass value. So pump 2 is H4 minus H3, and the combined pump work is WP1 plus WP2. So here we have combined, and the total turbine work is, so here we have from 5 to 6 we have 1 kg of mass working fluid, and from 6 to 7 here we have 1 minus x. So to calculate the efficiency of a Rankine cycle with when there is the regeneration process we include, so all the term we have calculated in the previous slide: Q1, pump work, combined pump work, and total turbine work produced. So the efficiency is the W net divided by Q1. W net is the work done by turbine and work consumed by pump. So here we have two pumps. So we have already calculated turbine work. So turbine is a work producing device, it has a positive sign, and pumps are work consuming device that have a negative sign, and Q1 is the heat supplied. So we will insert all these value into the relation of efficiency, and we can calculate the efficiency of a Rankine cycle when the process of regeneration is attached. So now if we want to calculate the amount of steam that is entering into the regenerator or feed water heater, so I will write it here. So in some problems it is mentioned as regenerator, and in some problem it is written as feed water heater, because it is heating the feed water, that is it is known as feed water heater. So this is schematic diagram. So apply the energy balance equation at the regenerator. So this is the regenerator. Here we apply the energy balance equation. So this is state 1, this is 2. Before the pump this is 3 state, this is 3 state. After the pump this is 4. After the boiler this is 5. After the this is stage 6. So this is 6, and this is 7 before the condenser. So this is state 6. So I have written all these states and labeled them. So now we apply the energy balance equation on feed water heater. So at the energy equation is S6 H6, X is the mass, and H6. So here in the schematic it is written as M. So m kg of mass, m kg per second of mass is entering through the state 6 into the feed water heater, plus 1 minus m. So here 1 minus m kg of mass is entering into the feed water heater is equal to H3 into X. So 1 minus m plus m is m will cancel out, and 1 into H3 of mass is exiting the feed water heater. So the main function is to calculate the value of x. So after simplifying, the value of x is H3 minus H2, H6 minus H2. So x kg of mass is entering into the, so x is the mass that is entering into the feed water heater. So this is a relation to calculate the stream or mass of steam that is entering into the regenerator or feed water heater. So these are the some advantages of regenerator: increase the cycle efficiency, reduce fuel consumption, and reduce the size of condenser. So I have already discussed all three one by one. I have already discussed these advantages in the previous slide as well. Now if you want to calculate the overall efficiency of steam power plant, so the overall efficiency of steam power plant consists of the efficiency of boiler, efficiency of Rankine cycle, efficiency of a turbine, and efficiency of generator. So briefly we will discuss these efficiencies. So we have already discussed about the efficiency of Rankine cycle. Here we have the enthalpy values written for each state. So for efficiency, to calculate the efficiency of Rankine cycle, we have H3 minus H4 divided by H3 minus H2. So efficiency of Rankine cycle we will calculate through this formula, and the efficiency of boiler is H3 minus H2, H3 minus H2 divided by mass of fuel. So this is the mass of, because here heat will be supplied into the boiler, so certain mass of fuel will be burnt, and the fuel have certain heating value. So we will divide with the mass of the fuel multiplied by heating value of the fuel. And the efficiency of turbine, so the steam will be striking the blade of the turbine and rotating, and these blades are connected with the shaft, and that shaft will be rotating. So the shaft output divided by mass of steam into H3 minus H4. So H3 minus H4 are the enthalpy difference through the turbine. And to calculate the efficiency of generator, we have a relation of 3600 multiplied by electrical energy in kilowatt. So the work electrical energy produced in the kilowatt. So and WT is the work done by the turbine. So these are the simple relations. So you will be given the value of these. You will find the efficiency of individual component: Rankine boiler, Rankine cycle, boiler, turbine, and generator. So then after calculating their individual efficiency, then you will be able to calculate the efficiency, overall efficiency. So the conceptual question answers. So you are advised to go through these conceptual question answers. We will discuss it in the class as well. So these are simple conceptual question answers. Can the energy removed in power plant condenser be useful? Yes, if the temperature of the steam that is exiting the turbine, usually we use the regeneration process discussed in this lecture, and the function of condenser to extract or reject the energy in the ambient. So if the as the working fluid is in the mixture of saturated vapor and liquid, it's a mixture, so energy extracted through the condenser can be utilized elsewhere. Numerical problem. So a steam power plant, so it's a steam power plant is shown operating on Rankine cycle, has a saturated vapor. So the pressure is given 3 megapascal, leaving the boiler, the turbine exhaust to the condenser operating at 10 kilopascal. So both the pressures of boiler and condenser are given. Find the specific work and heat transfer in each of the ideal component and the cycle efficiency. So we have been given the pressure value for the boiler and condenser. So against these pressure we will be using the steam table to find the other values as well. So first we will discuss the pump. So W pump is H2 minus H1 and entropy, because it's an isentropic process, so entropy will remain same. We use the work done by pump for open system. So because the mass is coming and going, exiting the pump, so specific volume against the pressure of 10 kilopascal, we will see the value of specific volume and the pressure difference. Here we have converted the megapascal into kilo, so 3000 minus 10, so 3.02 kilojoule per kg of work, specific work is given. So if you want to calculate H2 value, so enthalpy value of state 1 is will be taken out from the steam table, and H2 is 194.83 kg kilojoule per kg. And for the boiler, the specific now we have the specific value of H2 intermediate, that is was H2, and for H3 we will look into the steam table against the pressure of 3 megapascal. So against 3 megapascal we have 2804 kilojoule per kg of H3 enthalpy value, and for H2 we have calculated this in the previous step. So QH, the amount of heat that is entering into the boiler in unit of kilojoule per kg, is 2609. So the next component is a turbine. So turbine is, we know that the WT is equal to H3 minus H4, and it is also an isentropic device. So initially we will be calculating the value of steam in so dryness fraction, because in the turbine is a mixture. So here we will be using the relation for SF plus X into SFG. This relation we have already discussed. So we will be calculating, this is the dryness fraction or quality as well. So here we will be introducing the quality that we have calculated in the previous step. To calculate H4, H4 is 1958 kilojoule per kg. We will insert the value of 1958, and the work done by turbine in terms of kilojoule per kg is 845.8 kilojoules per kg. And the last component is the condenser. So QL amount of heat is ejected through the condenser into the ambient. So 1958 is the amount of heat that we have calculated here, and 191.81 is the amount of enthalpy. So 1958 is also the amount of enthalpy, 191 is the enthalpy that we have looked through the steam table that was also mentioned in the previous slide. So QL amount of heat that is ejected to the turbine is 1766.5 kilojoules per kg. So the overall efficiency is W net over QH, and the W net is the combination of turbine work and the work of pump that is consumed. So WT is 845.8 minus 3 divided by QH. Here we have calculated in the previous slide, that is 2609.3. So the efficiency of turbine is 32.3%. So that's all for this lecture. So all students are advised to go through example problem of each topic discussed in this lecture. So you must all go through your textbook, you go through your examples and the exercise problems as well, uh, for all the topics that are discussed during this lecture. You should write a handwritten lecture summary reports and send it to my email ID, that is arslan@ciitwa.edu.pk. And you should prepare this lecture thoroughly, because at the end we will be having a viva for each lecture. Thank you very much. Take care. Allah Hafiz.